Hi, and welcome to the Build Your Own Data Logger course, presented by WILDLABS and Freaklabs. This is the second part of Video 2 in Module 1. In the last video, we looked at peripherals, accessories, and parts of the circuit board including ports and interfaces, I/O pins, the CPU, and the differences between an MCU and an MPU. In this video, we'll look at two crucial elements in deployable devices, memory and power. Let's start with memory. There are different kinds of memory, but the two types of memory that we're concerned with are called random access memory or RAM and flash memory. Random access memory is memory that you can read and write data into. It's very fast and it's volatile, which means it loses the data when the power is off. The variables in our app will be stored in this memory, and for example, printline uses RAM. Flash memory, on the other hand, you can also read and write into. It's also very fast, but the main difference is it's non-volatile, which means it doesn't lose data when the device is powered off. And this is where our compiled application code will be stored. Standard Arduino comes with 2K of RAM and 32K of flash. However, for our purposes and deployment purposes, we need a little bit more memory because we need circuitry and code for power optimization, SD storage, and other functionality. So the WILDLABS uses the 1284P, which has got 16K of RAM and 128K of flash memory. The biggest consumer of memory is the file system, in this case on the SD card. ASCII text also uses a lot of RAM. Embedded applications tend to use CSV format, not JSON, to save room in the memory. So let's look at the specs of the 1284P. As I mentioned, it's got 16K of RAM, 128K of flash memory. It operates at 3.3 volts to 5 volts, which we'll talk about in a moment, and it has 32 input-output pins, including 8 analog pins. The analog pins are on sensor 0 and sensor 1. Now, let's look at power. Low power consumption is crucial for field deployable devices. The amount of power a device uses determines its lifespan, or how long it can stay in the field before it runs out of power. The lower power consumption, the longer the lifespan. Power consumption also determines how big the power supply needs to be, or how many batteries or how big a solar panel the device needs. In short, more power equals higher voltage, equals shorter battery life, or bigger batteries. So how do we determine the power consumption of a device? There are two power consumption modes that we're concerned with. The first is sleep mode, where everything is connected to the circuit board, but it's asleep, it's not doing anything. The second is active mode, where everything is connected and operating. So the question we ask is, what's the total current the system consumes in either or both of those modes? So what is current? Current is the rate at which electric charge flows around the circuit. It's measured in amps and amp hours. An amp hour is the electric charge that flows in an electrical circuit when a current of 1 amp is applied for 1 hour. For a device like ours, we'll be talking about current in microamps and milliamps. Hardware datasheets include how much current the peripheral component consumes. We can also measure the system current with a multimeter. And we use a quick back-of-the-envelope calculation to get a ballpark for lifespan. Then we test for real during the pilot phase. The calculation we use is battery current in milliamp hours divided by current in sleep mode in milliamp hours, and this will give us the number of hours before the batteries die. We then take that number and divide it by 2 or 3 to get a more realistic estimation of the battery life. For WILDLABS, the active mode is 45 milliamps. The sleep mode is 800 microamps, or 0.8 milliamps. This is a bit higher than usual because the SD card consumes a lot of current. WILDLABS runs on 1 AA battery, which equals 2000 milliamp hours. We have 3 AA batteries because we need higher voltage. So let's look at the calculation. 2000 milliamp hours divided by 0.8 milliamps gives us 2500 milliamp hours, which theoretically gives us 100 days of battery life on 3 AA batteries. We divide that by 3 again, and we get approximately 3 months. If you want to increase the lifespan of your device, there's a few power-saving tips that you can do. You can decrease the voltage the system needs or increase the battery so it has more power stored. You can make sure you have a real-time clock or calendar on the device so you can put the device to sleep and wake it up only when you want it to do something. And you can reduce the awake time of your device when it's actually doing things. Finally, let's talk a little bit about voltage and batteries. Voltage is pressure from a power source, usually a battery, that pushes the electrical current through a circuit. Voltage for hardware, for example the circuit board and sensors, is either 3.3 volts or 5 volts. And the voltage of peripherals, components in the circuit board needs to be compatible. Most sensors now are 3.3 compatible, for example the DHT11. The WILDLABS board uses 3.3 or 5 volts, but the sensor ports are on 3.3 volts. And WILDLABS, as we mentioned, uses 3 AA standard batteries, which gives us a voltage of 4.5 volts. So this all doesn't match up. Well, usually the circuit board has got circuitry which raises or lowers the voltage for a piece of hardware to make sure it all runs at the same voltage. There's lots more to hardware that we could go through, such as communications, but for now this gives you an overview of what we need to know for our data logger. So we'll leave it there. Let's get on to the software. That's it for this video. If you have questions, post them to the forum or bring them along to the fortnightly office hours. In the next video, we'll look at the software part of the design stack.